We've already looked at the graphs of sine and cosine. Previously, we saw the graphs of y is equal to a times the sine of x, or a times the sine of theta, or y is equal to a times the cosine of x, or y is equal to a times the cosine of theta. Remember that a, or rather the absolute value of a, is the amplitude of this function. And the amplitude is the distance from the midline of the function to its maximum point, or the midline of the function to its minimum point. We always report the amplitude as having a positive value. That's why we use the absolute value of a. Along the x-axis, we've graphed the angle in radians. So sometimes we've seen theta used along the x-axis. The period is the length of one cycle. We can measure this from maximum to maximum, or we could just as easily measure the period from minimum point to minimum point. Doesn't matter where on the graph we measure it. Maximum to maximum or minimum to minimum are just two of the easiest ways to do this. When we first looked at graphing sine and cosine, we looked at the values of the angle from 0 to 2 pi, or from 0 degrees to 360 degrees. And we looked at what happens at every pi over 4, or at every 45 degrees. We used a table of values to evaluate the sign of each of the values in steps of pi over 4 from 0 to 2 pi, and we used the output, the value of y, to then graph the function. So for an angle of pi over 4, we found that the sine of pi over 4 was 0.7. For an angle of pi over 2, we found that the sine of pi over 2 was 1, and so on. Now that we have a good idea what the sine and cosine waves look like, we don't have to graph every pi over 4. What we discovered was that the interesting things happen at the quarters of the function. So at the beginning, quarter of the way through, halfway through, 3/4 of the way through, and all of the way through the function. At the beginning, the middle, and the end for the sine wave, we have our zeros. We cross the x-axis. 1/4 of the way through the sine wave, we're at a maximum, and 3/4 of the way through the sine wave, we're at a minimum. Let's look at cosine. Again, we looked at graphs of y is equal to a times the cosine of x. And as for sine, the absolute value of a we called the amplitude, and we graphed the angle in radians on the x-axis, sometimes writing x on the x-axis or just writing theta. Cosine is similar to sine. It's really just shifted to the left by pi over 2. Looking at an angle of 0 to 2 pi, we find that cosine starts at its maximum and therefore ends at its maximum. Halfway through the function, we're at a minimum. 1/4 of the way through the function and 3/4 of the way through the cosine function, we're at the zeros. We cross the x-axis. As for the sine graph, we had used a table of values to graph our first cosine graphs. But now that we have a good idea of the function, we can just remember these critical points, where we find the maximum and minimum values and the zeros for the graph of cosine. Again, I've highlighted a single period here. This repeats in both directions. Now you'll notice here that the graph, as we saw for sine, is that of y is equal to 1 times the cosine of x. The maximum value we get to on the y-axis is 1, as is the minimum value. That means the distance from the center of the graph to the maximum, or the center of the graph, the midline, to the minimum is 1, or a has a value of 1. We saw that when we change the value of a, the shape of the graph doesn't change, the general shape of the graph doesn't change. We simply change where our maximum and minimums are. If a had a value of 1/2, for example, if we were graphing y is equal to 0.5 cosine of x. The maximums would be at y is equal to 0.5. The minimum would be at y is equal to negative 0.5. And the zeros stay at 0. So we'd have a graph that has the same shape, it's just compressed in the y direction. Now it is time to get a little bit more complicated. Here is the entire structure of the sine function. We'll look at the same thing for cosine. On this slide, we'll start by looking at b. So we've previously looked at a. So now we'll look at graphs that have the form y is equal to a times the sine of bx, or y is equal to a times the cosine of b times x. We'll look at c and d separately. B is the frequency. B tells us how many times the cycles, or how many cycles, will fit into 2 pi radians. B is the frequency. B will tell us how many cycles fit into 2 pi radians. For the graph pictured here, this is cosine, we find that we have one cycle and then a second cycle that fit between 0 and 2 pi. So the frequency of the graph pictured here is 2. If we're given the period of the function, we can calculate the frequency and vice versa. So if we're looking for the frequency, we'll use 2 pi divided by the period. If we are looking for the period, we'll use 2 pi divided by the frequency. In this case, in this graph, because we have a b value of 2, we have a period equal to 2 pi over 2, or just pi. And we can see that here. You can see that in both yellow and orange, that it takes us from 0 to pi, or from pi to 2 pi. It takes us a distance of pi to get through one cycle of this graph. Moving the other way, if we find that we have a period of pi over 2, for example, we can calculate the frequency. So the frequency is 2 pi divided by the period. That's 2 pi divided by, well, we're told we have a period of pi over 2, so 2 pi divided by pi over 2. That's a complex fraction, but we know how to deal with those. Let's rewrite this as 2 pi divided by pi over 2. We can't divide fractions, but we can multiply by the reciprocal. So we find 2 pi times 2 over pi, and find that 2 pi divided by pi. If we're instead given the frequency, we can use the same formula to calculate the period. We'll simply rearrange the formula given on the left. To calculate the period, we take 2 pi and divide it by b. In the case of this question in the cloud, we have 2 pi divided by a frequency, a value of b of 1/2. That's a complex fraction, so rewriting that as regular division gives us 2 pi divided by 1/2, and multiplication by the reciprocal gives us 2 pi times 2 over 1, and 2 pi times 2 is 4 pi. This means that if we have a frequency of 1/2, that is, in the distance between 0 and 2 pi, we get through 1/2 of the cycle of the function. This means it will take us from 0 to 4 pi to get through the entire cycle. So far, we've looked at the amplitude, which is given by the absolute value of a. We've looked at the frequency, which is dictated by b. And by knowing b, we can calculate the period, as we just did. So now we'll have a look at c. Given our general equation for a sinusoidal function, either sine or cosine, we find that c is the horizontal shift, or the phase shift. It shifts the graph along the x-axis. If we think back to quadratics in vertex form, these have the form y is equal to a x minus h squared plus k, where the vertex was given by hk. C functions in the same way that the h does. In the case of quadratic, the h shifted the quadratic left and right along the x-axis. What we see is a regular sine function, such as this graph of y is equal to 1 times the sine of x, can be shifted. In this case, each value is being shifted a distance of pi over 2. So this point has been shifted from 0 to pi over 2. This point has been shifted from pi over 2 to pi. So this is the graph. This shifted graph has the equation y is equal to sine x minus pi over 2. As we saw for h, when h appears to be negative in the function, the shift is to the right. Similarly, if we have x minus pi over 2, we see a horizontal shift to the right, or a horizontal shift of positive pi over 2. Finally, the value for d gives us our vertical shift. This shifts the graph not in the x direction, but in the y direction, or up and down. But we're not going to cover that in this module.